Whenever you're ready. Okay, so this is long animation frame status update. First things first, this is LoAF, not low, no brain involved. Sorry. LoAF also in Hebrew means doesn't fly. Which I thought of that. Yeah. Side note, it's also Noam and not no. Okay? Easy to remember, LoAF, Noam, LoAF. Okay, done with the Hebrew stuff. Okay, we're going to do a quick recap of what LoAF is, talk about what's been done, what's kind of ready, where's our classes that are here, relationship with event timing that we had a lot of questions about from some people in this room. What's missing also, what we learned from people who are already using it with Origin trial and what kind of feedback we got. And what do you think? And hopefully a conversation a bit about this. So quick recap. This is where we kind of started. We want a web that's more responsive, that like you click things and they respond rather than junk and like wait and slug and whatever bad words you can find for this. So as part of speed metrics, in order to have a web that's more responsive, we want to measure what makes it less responsive. So we want to measure sluggishness. So great, we have INP. We talked about this yesterday. We can measure regressions in responsiveness with INPs, seeing what's the worst interaction, the times between interaction and pain. Okay, but this is a regression metric. It tells you how well you're doing, but what caused the INP? How do you find out how to improve it? How is it become actionable? So let's look from our many accumulated hours, years of tracing of what causes sluggishness. There's can divide it roughly to three main things, probably more, but it's a good rough start. One is a very direct, slow event processing. It's pretty clear. You have a click event, you're doing something very long, it takes long to paint it, it's a bad INP. Second one is main thread congestion. You're simply doing a whole bunch of things in the main thread that are not necessarily related, and they make your event delayed. The third one is other, all kinds of things that happen in the system. Compositor, you have a generally compute pressure, the high compute pressure on your machine, your input handling is slow. We're talking about the second one. The idea here is to measure the second one in a way that's actionable, main thread congestion. So up until now, we had long tasks as a way to do this for quite a while. That's great, but there were three issues that we found with long tasks after several years of using them or seeing people use them in the field. The first and main one is that tasks are an artificial term. They're something that is internal to the browser in a way. It is mentioned in the spec, but many times tasks are used for multiple things, and they're not directly connected with UX. And many times we found, at least in Chrome, that exposing task length exposes implementation detail that's not necessarily useful. Something about tasks is a bit too internal. The other thing that was more of a missing feature with long tasks is that they don't have attribution. They have window attribution, but it doesn't tell you what happened in this long task to make it long, just tell you that there is a long task. So here comes long animation frames, which we see as long tasks version 2, if you. So a long animation frame is the time between idle and paint, or between the end of the previous frame until the end of this frame. Time where you had nothing to do until you finished painting. This is the cycle, the life cycle. You start with idle, you maybe do some work, let's say process a fetch response. Then you check if you need render. If you didn't, if 50 milliseconds or more has passed, then yes, this is a long animation frame, even though we didn't paint anything. Just a long, in this case, it's just a regular long task with no paint. If you did render, we wait until the next render. We perform the rendering work, and if, at this point, the whole thing took more than 50 milliseconds. This was a long task. In terms of the HTML standard, you can say that this is the time from beginning of task until after the next updated rendering. What we provide in LoAF. Apart from the length itself, we can tell you how much of it was done work versus rendering, which we couldn't do in a long task because it's too discrete. Like you don't know what rendering, like there is no rendering task just in spec. We know if LoAF was blocking feedback. We know if there was layout thrashing or style thrashing inside the frame and how long. Also something we couldn't tell in long tasks because we didn't know if the style and layout was actually the one you needed for the end. We have to wait until rendering to know if style and layout changes from before the rendering were the last ones. Also, we give information about scripts, which scripts were run during the animation frame. The scripts are actually script entry points, is where the web platform meets JavaScript. We don't profile your whole script to find which was the longest one. We just look at the, you can say, top of the stack. Event handlers, callback, like set timeout callback, promise resolver that are at the beginning of the task, like the fetch, and script blocks, like code. Those are the four types of those LoAF scripts that we have. For each script, we can expose how long it was compiling versus executing, while just doing layout thrashing versus pausing for things like sync XHR alert. We also give the source location of the script in as much as we can without creating overhead and which type it was. What's been done so far in this feature? So most of this is implemented in Chrome to the degree of it's an end. Currently, we're on Origin trial, meaning anybody can register their web page or library to enable this feature. We actually have several active participants that are providing feedback. I'll share a bit. One is the RAM Vision. They already provide this in their dashboards. So they tell you that you have bad INP. Here we found a script that might be the cause of this bad INP. It's very initial for them because it's an experimental feature. This is what they said. Wait, not moving to the next slide.
Yeah, poor response.
Yeah. Yeah,
That's a network here is potentially.
sure. Yeah.
Are you on the million network on or
Yeah, it's easy to pick up.
the DPAN?
Anyway, I think I'm going to continue for a bit without the presentation. Yeah, from RAM Vision, said a game changer, making it easier to pinpoint and troubleshoot the IP issues. Second one, got a big productivity suite that's using this in the field to find scrolling junk. And they making disconnected. Okay.
Do you want me to try to
Rejoin.
one second, let me try to rejoin. See if it loads.
I think it might be a Zoom issue because I'm not getting the stream locally from anyone's camera. Like we see it up there, but I'm not getting it.
Yeah, I think it's just the network, definitely, but
Can you hear us on Zoom?
Yes.
Yes, and we can see you and the cameras. The stream is live.
Okay.
okay.
Okay. Um,
I'll get into Ethernet.
Yeah.
Yeah.
Thank you for
Well,
that.
like my. I will, so I don't.
Oh,
Okay, third case study, a third-party ad provider. They're using it to see if they don't want to regress to be the cause of bad responsiveness issues in the first party that embeds them. So they're doing field regression testing on whether they are the cause of bad INT for their customers. I think this is very exciting if ad providers start caring about this. And I think giving them something actionable would help them take responsibility for this. A relationship with event timing and INP. We found that trying to match INP and LoAF directly is a bit of a red herring. It doesn't always give you the results you expect. I see it a bit like trying to figure out what caused traffic congestion by following one car on the road in the city. It doesn't really tell you the whole story. It might incidentally tell you the whole story. But user experience of a single car doesn't always tell you the same story as looking at the city from above and finding the congestion points. And the way I see it is like this. It's a cause versus impact. You have main thread congestion and you have sluggishness. And in some cases, they coincide. We measure sluggishness with event timing INTs. Those are user experience metrics. And we measure main thread congestion with LoAF. And to find the bit in the middle, it requires some analytics, some analysis, and it's not. This analysis could be different for different sites. Could mean different things for different sites. A similar case for this is element timing and resource timing. Element timing in LCP can show that you have a slow user experience. It's like a UX regression metric, and you have resource timing to show you why this happened and to show you your loading efficiency and your network protocol or whatnot. A lot of things work together. We didn't want to merge. It's intentional that they're not merging into one. To not try to measure UX and like cause and impact with one metric. What's missing / next? First of all, gotchas that we found with the LoAF. We can't 100% cover all scripts because of LoAF. We do our best, but sometimes it can be misleading. And there's some education challenge in teaching people that it's kind of, you can't have a direct line between LoAF and blaming a script for bad responsiveness. It has to have an analysis It just gives you hints and data, and you can have an analysis in the middle, but don't just use it to point fingers. For example, in the wrong vision slide, they had a page that uses a Sentry, which wraps all your JavaScript calls. It doesn't mean that Sentry is to blame for performance. You need analysis to understand the site. Also, there are lots of reasons for congestion that we're not allowed to expose to the web, like the cross origin frames that happen to run on your same process, or system congestion, or things that extensions do that are privacy. Okay. So we're right now, those are just you know you had the LoAF, but you don't know why. Not great, but missing things in LoAF. We want a clearer story about how this relates to event timing and how to perform such analysis. So that it actually helps you with INP and with responsiveness. We want to connect it better with Lighthouse DevTool, TBT. Yeah, and we want to fix the whole script entry attribution to less partial. So the next step is to finish the origin trial, fix those missing bits, analyze correlation with INP. I think we already presented this in a web working group, and we're presenting it now. This means we'd love to have as much conversation as possible with you guys that are not part of the Chromium endeavor, but I think that also after these we'll have more data to share. So it's really up to you when you join in and what kind of information you put into this. But I think our focus on interop and like speccing into the fullest, etc., would be after we learned a little more about this. The takeaways. And responsiveness and congestion are related and separate. LoAF is what we see as the next generation metric for congestion after long tasks were there for a while and we found limitations with them. There's still work to do on the metric itself and on how to analyze it. Right?
Recording in progress. Take it away.
Ready? Yep. Okay. So hi, everyone. I am Scott Hasley. I work on Chrome at Google. So today I'll give you an update on scheduling APIs. This topic is something that I've presented to the group in the past a few times, but looking back, it's been a little while. So I thought today we could just kind of do a high-level update, talk about things that we've done and where they're at, the things that I'm working on now, and things that we're planning to work on next. So just to kind of get started here and provide a little context of like why, why does scheduling matter for performance? Where can it be impactful? When I'm thinking about scheduling, I typically think about periods of contention. In this case, thread and more specifically main thread. But this principle kind of holds true for other resources as well, network, et cetera. Like when there's more than one thing to do, which happens during periods of contention, scheduling gets a lot more interesting because we have choices to make, and those choices can affect performance. So we do see, kind of bursty behavior on the web at times, specifically during loading, single page app navigations, periods of interactivity and input handling like typing, et cetera. And this is where we think scheduling can have kind of an impact. So two main tools that we'll kind of talk about repeatedly here for doing scheduling on the web are breaking up work and prioritization. There are other approaches as well, obviously, to improving performance, including other scheduling things like offloading to a worker and just reduction in general. But here we'll talk about for tasks that must run on the main thread and need to be as long as they are. So breaking up work is something, it's interesting because this is web. We have run to completion semantics in JavaScript, meaning we can't preempt JavaScript tasks, unlike other platforms where you may be able to preempt the thread. And this is kind of a fundamental constraint where if input comes in at the start of a long task, we cannot process it. We have to wait for that task to complete. So strategy that is often used, or we hope is often used, is breaking up that work into smaller pieces such that the browser might be able to process input. And that's where that type of approach really helps with responsiveness. User perceived latency on the other side, another type of latency. Here I'm talking more about like end-to-end latency. Like what is it that like, what's the user trying to do? Like you've clicked a thing and now we need to maybe fetch some data and then show a thing. There's this kind of like end-to-end latency involved, or maybe it's just the task that was getting broken up in the first place. So if this is where scheduling traditionally comes into play, where we can reorder things, and how we choose to order things can have an impact on user experience. So if we prioritize things that are on the critical path or deprioritize things off of the critical path that don't need to be there, we can improve performance. And I'll note here a couple things. One is that these strategies, at least in Chrome in the browser, have proven very effective as well. For example, we try to keep any tasks that are on the main thread that might block input as short as possible. And also input tasks we prioritize. So given the choice between input and say a timeout, we're always going to pick input because responsiveness, you kind of have a short window. And then last, I did want to note that, and this will come up a couple times here, especially with yield, is that there's a little bit of overlap between these two things. So we know we need shorter tasks in order to have good responsiveness. But once we start breaking up those tasks, how do they get scheduled? If those tasks just go to the end of the queue that they're associated with, then the scheduler may choose other things before that. But introducing a notion of priority gives some control over that. Okay, so moving on, I'll talk about post-task. This is the API I've talked most about with this group, over the years, I suppose. So I'll just give kind of a quick recap and then status there. So this is, kind of all about prioritized task scheduling. It's a tool that developers can use for both responsiveness and latency, kind of just in the way that I mentioned. You can use post-task to schedule parts of the task, example on function boundaries. So you can kind of schedule subtasks, breaking these long things up into chunks. And then you can apply, if you want, a priority to those pieces, which lets you control a little bit of that end-to-end latency. If the parts of this task aren't that important, you can, mark them as background and they'll run, after hopefully important things. Or if they are important and shouldn't be preempted by other tasks, then, if you want that task to finish as quick as possible, you can mark them as such. And that priority is used by the event loop for scheduling. Just a couple other details of the API. It is a modern API in that it returns a promise, so it works nicely with async await. If you schedule a bunch of tasks, you can promise .all and wait for them to finish. It also takes an abort signal or a task signal, which is a subclass of abort signal for cancellation. And task signal can be used to express priority and also dynamically reprioritize. So similar to the slide that I've showed in the past, this is kind of the basic API shape. As I said, it returns a promise. You give it a callback, optionally a priority. And also we have this task controller abstraction that its signal will encapsulate both priority and cancellation. And you can pass that to post task and also other async APIs like fetch, and then cancel everything kind of en masse. So status for post task, like I said, this is something that we kind of started working on a while ago. We shipped this back in M94, and importantly for this group, since the last time I presented this, I think we were in origin trial at the time. We shipped this with no API changes since the last update that we had talked about. The usage has been kind of trending up lately. I think as Chrome kind of, as we're focusing more and more on responsiveness, and this is a tool that can help with responsiveness. we've seen the usage rise a bit to about 1.25% of page loads the last time I checked. I think it's been incorporated in maybe some third-party libraries. Recently, I've seen it used on some news sites, etc. So also, I think maybe since we talked last, we have a polyfill up on our Google Chrome Labs GitHub and also on NPM that kind of polyfills the entire API shape, so you can use this in browsers that don't support it. Okay, so want to move on to scheduler.yield, and this is what our current focus is. And this is also, because of that trade-off I mentioned, this is dealing with both responsiveness and latency, but this is mostly geared at an ergonomic API for improving responsiveness. So yield here means yield to the event loop. Yielding to the event loop gives us a scheduling opportunity. When we have a scheduling opportunity as the browser scheduler in the event loop, we're able to choose other potentially more important tasks like input, which is where the responsiveness angle comes in. So here there are typically two approaches. We can schedule tasks kind of on function boundaries. So imagine you have one long synchronous task that just makes a bunch of function calls. We can kind of schedule those function calls with post task or similar on those boundaries, and now we've broken up that long task. That's not always easy to do. From what we've heard, that's a lot of times what you want to do is just kind of pause the current task and continue on. It's conceptually all the same task. You want this just insert a yield point, yield, and then continue where you left off. So this is the pattern that scheduler.yield addresses, and two main goals here. This link here is into the explainer, so there's a much longer explanation of all of this. But the main goals here is we want obviously the UA to stay responsive to input and any other higher priority work like rendering that's associated with input in order to optimize IMP, for example. But also we want better performance over alternative approaches like set timeout, which I'll go into detail in this next slide here. So I think actually I presented this idea a long time ago, and it's kind of come back. I think this was WebPerf face-to-face like a few years back. We're talking about this idea, and we've heard it more and more from web developers, first-party frameworks, third-party, like everyone, that often very hesitant to get up the thread because of that trade-off that I mentioned, where if we do, let's say we insert yield points, we might have to wait until everything's scheduled to run before getting rescheduled. So for the input problem, without yielding, it looks something like that top diagram where we have this long task. Well, let's say input came in kind of early. We couldn't handle the click because the long task was running. After that, if the browser has this ability to do prioritization like we do in Chrome, we'll process input. We'll try to render as soon as possible, and then maybe we'll run that timer that was scheduled. But with yielding, the middle diagram kind of shows the problem of what developers are concerned about is that, okay, let's say we yield early because either we know there's input or we just broke things up kind of on function boundaries. We process a chunk, the input and rendering happen, but let's say we use set timeout for that continuation, as it's called. Well, there was already another set timeout that was pending, and it's going to go ahead of our continuation. So now the end-to-end latency of that task got really long because the timer, the set timeout there, the gray one, got an advantage that it didn't have, with that task not yielding. So with yielding and continuation, the idea is we'll prioritize continuations such that when you use this yield API, we say, okay, you're continuing the task, you already started running, we're going to give you a higher priority in the event loop such that after the input and render are processed, we can resume with that continuation. The set timeout runs when it was originally going to run in the first example, and we've mitigated some of that effect on latency. So basic API shape here is, I think the last time we talked about this, we were maybe kind of going back and forth on different ideas. What we settled on is just to kind of make this really work well with async tasks and just be able to insert these yield points wherever necessary in the long tasks, or wherever feasible. So you might have a task that does some synchronous chunk. You await scheduler.yield. By default, that's going to give it a little bit higher priority, like I mentioned, and then you can continue on, and it's guaranteed to continue on in a new task. By doing so, you create a scheduling opportunity, and the rendered scheduler can choose higher priority work there. Also, it takes the same options as post tasks, so you can, if you need to, express finer grained control over the priority of resuming. So for example, if the first part of the task is really important, but you want to yield at a background priority, for example, you can do that. You can also pass a signal so that you can abort continuations, just like you can tasks or pending network requests with fetch. Okay, and then the other bit about yield that I just wanted to mention, and maybe this could be a topic for a longer topic at some point for discussion, but yield also supports inheritance, which is something that we chose not to implement for post task, where you may be spawning new, somewhat unrelated tasks. Here, conceptually, the start point of the task and all of the continuations that you do with yield, let's say, for example, you're yielding in a loop, are really conceptually part of the same task. So if that task was scheduled with a priority, and it was scheduled with a signal, whether it's a abort signal or task signal, there's a good chance that should apply to everything in that task, if you're breaking it up or not. So to accomplish that, we have this idea of inheritance, where you can inherit the current signal or priority specifically for continuations. This is going to work across arbitrary promise boundaries that I'll show in the next example. We also made this work with request idle callback. So that will resume at a background priority, since idle tasks are already low priority to begin with. And this is something, just because of how much sense it makes conceptually, and we think that generally this is the right thing to do, we're considering making this the default for the API, which will only come into play if you're using it in conjunction with post task or request idle callback, which are the APIs in which you can express priority. So as an example, here I just have a task controller that's background priority. You schedule this task with this signal, and this task does kind of a loop here over a bunch of items that it has. And it's awaiting the item, which is just a function. That function itself may be asynchronous, and it might yield to the event loop. Let's say it does the fetch, or etc. No matter what that does, each time you await yield with inherit, that is going to always do the continuation at the background continuation priority. So that's kind of how that works. And since background task was scheduled with a signal, if that controller if you were to call controller.abort, that promise will reject should there be one pending for the continuation. I just wanted to make sure we covered that, which is the kind of major difference in the API shape for the options between post task and yield. Okay, so status here for yield. We have this in origin trial right now in Chrome. It started it's M115 to 118. I think 117 is rolling out to stable. So we're just kind of right in the middle of it. We're probably going to extend this at least a couple milestones because of what I'll mention next. But I did want to say that main question we're looking at here is, what does this do to site metrics for folks that are trying it? Did this help with that concern about if you give up the thread, you're letting too many arbitrary tasks run? What does it do for responsiveness? On the other side of that, by prioritizing continuations, are we prioritizing them too much? Is there important work that's being starved? And that one is something that could happen, not necessarily if you're taking something that was long and not yielding in the first place, but if you're changing your yield approach where it was using set timeout or post message, for example, and now you're doing it in a prioritized way, does that have negative effects? So these are the things that we're trying to understand through the origin trial. Facebook, I think there may be some Facebook folks there. Many thanks for trying this out early. They had a fork of the React scheduler that replaced the scheduler with yield. And we did see the latency improvements, to some degree that we were looking for, in that the end-to-end latency of some user interactions did decrease, which is what we were looking for. So that's an encouraging sign that it's meeting that goal. It also fleshed out a bunch of some edge case bugs that we needed to fix in 117. So I think we might be rebooting that in 117 or 118. Also, we just sent out some origin trial instructions, I think, and we had quite a few signups recently, a mix of first parties and third parties. So that's why we're probably going to extend it for at least a couple of milestones. Hope to get a bunch more feedback there. So maybe once we have all of that feedback, I can represent to the group on how things went. Okay, in the time remaining, I'm just going to kind of briefly talk about what we're looking to work on after yield. Here, more yieldy APIs. So something that comes up a lot in the context of responsiveness and INP is you have an input handler. You want to show some initial UI update that's like, hey, I'm processing this input, but you want to yield, but you don't want to block rendering. And that can be a little bit racy because vsyncs and frame rates and all of that. And there's not a guarantee with yield like that that next paint is actually ready yet. So the idea here is a very similar yieldy API that has the semantics that it will wait until rendering happens and then resume. So here in this example, it's a guarantee that after that initial response, it's not going to continue processing that input until after the rendering completes. As I said, this is kind of really important thing for input handling. It can replace, I mean, to some degree, it's just a bit of sugar on top of, like a double RAF or a RAF plus a post task, et cetera, but it's a lot more ergonomic, we think. It can also be optimized, unlike the double RAF, where like if the DOM is clean, there's no RAF pending, you may be able to just not schedule the frame and continue with the yield right away. And with the page hidden, this would act just like yield, because in that case, there's not going to be a rendering update, so there's no need to wait on it. And then functionally, the same options and priority semantics as yield has. Wait was another idea, and again, these are just kind of like things we're thinking about. This kind of comes from like this idea here is that you're going to wait. You want to yield, but you need to wait for the condition, and that condition being like time. So you want to wait for some timeout, which can happen like with polling when that's necessary. So here's a basic example of what that would look like. This is again a little bit of sugar, and this is something that's been very often requested from web developers. Is we'd really like a promise-based callback with set timeout, just to make this. We just want to wait and continue in the same task. So that's kind of the idea there. The difference here being that we don't think it really like yield. It's kind of it's a bit different in that there's an element of time here, so it doesn't necessarily need to be prioritized in the same way that yields are. So we weren't planning on giving this a priority boost by default, but it has the same options as yield, so you could specify a priority and do inheritance there as well. Okay, and then finally, a bit further out, something that we're looking at, extending the priority system to other APIs, specifically to some I/O. Again, just kind of ideas, but the key thing here is that the APIs that I've talked about, they they don't cover the full set of event loop tasks. So while you're yielding, for example, you may be waiting on data that's very important, but there's no way to express the priority of that fetch other than the network. Like we can do network priority, but not main thread priority. So if we're in a period of contention, like a spawn navigation, it may be really important that the data may be on the critical path. So, we're just thinking about ways and APIs that might make sense here to extend this to. So fetch, asynchronous script, storage we've heard for things like Drive and maybe other storage types of sites. Like there's things that are on the critical path that involve storage. Message channel is another one where you may be offloading to a worker, and when that data or whatever it was doing is ready, it's really important, but we don't really have that information from the browser scheduler point of view. So, and that is it. I don't know if we have any time remaining, but if we do, happy to take questions. And specifically, I'd be curious if there are any of these topics that the group would like, a little deeper dive into in like a call or something like that. So thank you very much.
Thank you. Let me. Take it away.
Yeah, so I was going to bring this up. Like maybe this is something we just push off till the charter discussion, or we kick off like start of the conversation for the charter discussion. But the general idea is like the concepts of reliability and web perf. Like it's right now reliability isn't really owned anywhere in any working group, and the conversation came up in the crash reporting repo. Is should this be in scope for web perf? Is crash reporting the type of thing that makes sense in web perf? And then is that a charter thing that would need to be adjusted or anything like that? I don't really have much more than this like quick prompt. The kind of topic that led to this is like, what's the line between performance and reliability? Most of the times, many of the things that we talk about with reliability are tied tightly. A hang is kind of an extreme long task in many cases. A out of memory crash is just extreme, not just, but can be extremely poor memory usage. Similar to kind of compute pressure or network error logging or a handful of these other areas where it's like an error or reliability issue occurs as the result of a performance issue, tends to be correlated in many cases. And the reason this came up was we were looking at kind of unresponsive reports for crash reporting and including a stack as part of that, which ties similarly to like it's an extreme long animation frame if it leads to a hang. And we were looking at that general space. So like that's my like quick the topic I wanted to hit. I don't know if we just want to kind of table till we talk more about charter or if we want to talk more about it now, but that's the general thinking.
Okay, thank you. And I think, yeah, so I'll stop the recording.